Hi everybody and welcome back. I hope you all had a nice spring break last week, enjoyed the nice weather, and it didn't feel too short. It always feels a little too short. But this week we're back, and what we're going to be looking at this week is our first real application of the sampling distribution and some of the other things that we've been looking at over the last couple of weeks. So the topic today is confidence intervals, and I'm going to explain what that means. So when we're talking about sampling distributions, when we're talking about confidence intervals, we're still talking about inferential statistics, where our goal is to take a sample, so some data that we have in front of us, and use it to learn something about a broader population that we can't actually see in front of us. So if you wanted to learn about people's attitudes about appropriate sentences for different crimes, you could take a sample of some number of people, ask them how they think things should be sentenced, and then use that sample of people to try to generalize to maybe what all people in New Jersey or all people in the United States would think. And when you take a sample, you get something called a point estimate. And the point estimate is your best guess based on that sample. So let's say you take a sample of 100 people, you ask them how many years they think a sentence for robbery should be, and your average sentence length that people say is 10.6 years in your sample. So you asked 100 people, and the average sentence length that those 100 people gave you was 10.6 years. So what you know, and what you absolutely know, is that in your sample of 100 people, the average preferred sentence length for robbery is 10.6 years. But what you want to know is what people in the United States think the sentence for robbery should be. And so you're trying to use this sample to learn about attitudes about sentencing in the larger population. So if you have a mean sentence length in a sample, that's your best guess about what the true population value is. And we call that best guess a point estimate. So you're taking one sample, you have this one data point, which is the sample mean, and you're trying to use that to learn about what the overall value would be in the population. So if we're saying we have a sample of 100 adults from the United States, you ask them all what they think the sentence for robbery should be. They say on average it's 10.6 years in your sample. Your best guess for what the average sentence length for robbery that people would want it would be in the United States overall, your best guess for that would be 10.6 years based on your sample. So again, your best guess is your value that comes from a sample, so some kind of sample statistic, that you're using to try to make an estimate for what the real population value is. And if you're using simple random sampling, which in this class we're assuming is always the case, on average a point estimate is going to be right. So that means that if you were to take lots and lots of samples of 100 people, calculate the mean preferred sentence length for robbery in each of those different samples, on average, across all those different samples, you're going to come to the right value. So the true value that people in the United States think is the right sentence for robbery. And we saw this last week, right? So I did the multiple samples using the number of letters and names and people in the class. And you could see that across all those samples, we got a bunch of different values, but then when we took the average of them, they all sort of converged on the right answer. So it's the same idea here. But the issue when you're using one sample to learn about a population is that you're only looking at one sample. And because sampling involves random chance, it's always possible that the sample you're looking at just happens to be unusual. It's not likely, but it's possible. So it could be that if you're trying to learn about attitudes towards sentencing in the United States, you take a sample of 100 people, and you just so happen to have some people who are really, really punitive towards crime. They just want people to be punished for crimes. And if you were to look at the average sentence lengths in your sample then, they would be higher than the true preferred sentence lengths in the population. Because you'd have some people in your sample who just happen to be pulling that average up. The opposite could also happen. You could just so happen to have several people in your sample who, think the criminal justice system's totally screwed and they want nobody to be sentenced for anything ever. And that would probably pull your average down, because you'd have some people in your sample who are less punitive than a typical person in the United States. But then the issue is you're only looking at one sample, so you don't know what it is. It could be that it's really close to the true population value, or it could be that it's not. And the way we get around this, and the way we use samples to make inferences about population values, is through something called a confidence interval. And what a confidence interval does is essentially creates a buffer around your point estimate that tells you some range of values that most likely includes the true population mean. So again, it creates a buffer around your point estimate, so that estimate you're taking from the sample that most likely includes the true population mean. So you'll be able to look at one sample and based on that sample come up with some range or interval of values that most likely includes the true population mean. So if we're thinking about preferences for sentencing in the United States, you'll take your sample of 100 people, ask them how they'd sentence different crimes like robbery, and then you'd be able to say, there's some range of years that most likely includes the true preferred sentence for robbery among people who live in the United States. And I'm going to go through an example using some actual numbers in a bit, so I'm not going to just throw numbers at you right now, but that's the general idea behind what a confidence interval is. So I have most likely bolded there, where most likely, we're saying what's a range of value that most likely includes the true population mean. A nice thing about confidence intervals is that you, or me in this class, get to decide what most likely means. So do we want to be 90% sure that our interval includes the true population mean? Do we want to be 95% sure? Do we want to be 99% sure? Do we want to be 99.99999% sure? Totally up to you. And you can calculate different confidence intervals based on different levels of certainty. Those levels of certainty are referred to as confidence levels. So in other words, how confident are you that the interval you're calculating includes the true population mean? And do you want to be really certain that your interval includes the true population mean, or are you okay with a bit less certainty? And where you see the confidence level when talking about confidence intervals would be in a statement like this, where you would calculate a confidence interval. If you say you're doing it at a 95% confidence level, we would be able to say that we can be 90% confident that the interval we calculated includes the true population mean. And another way to think about this would be that if you have a 90% confidence level, if you were to take samples and calculate confidence intervals 100 times, 90 of those times, so 90% of your different attempts, 90% of those times your interval would include the true population mean. Common confidence levels that are used in research and that we'll mostly be using as examples in this class are 90%, 95%, and 99%. As a quick note here, and this is where it's important to be precise in language when talking about these, because when you're dealing with math, different things that sound very similar often mean very different things. So when dealing with confidence levels, we're always talking about how sure we are that our interval is, includes some value, that it's in the right place. But you don't say that you can be 95% confident or 90% confident that the true population mean is inside a particular confidence interval that you calculate. The reason for this is that if you calculate a single confidence interval, some range of values, so let's say between 10 and 12 years, you've got some range of values. The true population mean is either in that range of values or it isn't. And there's no probability or certainty involved in there. There's some true population mean out there, and either it's in your confidence interval, which means there's a 100% chance it's there, or it's not in your confidence interval, which means there's a 0% chance that it's there. So regardless of whether you're with me on that, just take my word for it that you would never say that there's a 90% chance or a 95% chance that the true population mean is in your confidence interval. Instead, you say that you can be 90% confident that your confidence interval is in the right place and that it includes the true population mean. So you might ask, we can calculate these different confidence levels. Why would we not just go for the most confidence that we can have every single time? Why wouldn't we just try to be 99.999% confident? The answer to this question is that there's a trade-off. And the more confident you are, the wider your buffer around your point estimate is. So if you're really, really, really confident that your interval includes a population value, it has to be a pretty big interval. If you're willing to be less confident, you can come up with a smaller interval. So in other words, a smaller buffer zone around your point estimate. So for example, in this preferred sentence length for robbery example that I'm talking about, a 90% confidence interval would be smaller than a 99% confidence interval. So we might be 90% confident that the true preferred sentence length is between 10 and 12 years. We might be 99% confident that it's between 8 and 14 years. And those are made up numbers, and I was going to try to not throw them at you. But the idea is that the more confident you are, the wider your interval has to be likely to include that true population value. Also, I have a small head, but I realize that when my hands are up here, it's like just catch it in there. And I put that at the end of the slide, so I can't even get rid of it. So there you go. That's what goes on in my head when I'm not doing this. All right, so how to find a confidence interval. There are 2 steps to finding a confidence interval. One of them is going to be to determine something called the critical value of z. And this sounds really complicated, but in actuality, this is going to be one of the easier things that we ever do in this class. And then once you have that critical value of z, you're going to use something called the confidence interval formula, which I'm about to give you on the document camera. Before I do that, though, I'm just going to throw this table up here that I'll be explaining and making a little bit more sense of in a bit. But this is a table of critical z-values and the confidence levels that they correspond to. And when making confidence intervals, there's never any calculation involved in finding a critical value of z. Instead, you use the same critical value of z each time you do a 90% confidence interval. You use the same critical value of z every time you use a 95% confidence interval, and you use the same critical value of z every time you do a 99% confidence interval. And since those are commonly used confidence levels, I have them listed out here. So you can just refer to this table anytime you see one of those different levels of confidence. But I'm now going to explain why that's the case and where those values come from, and then what we're going to do with them.